All right, today we'll do some more SIMD vector instruction sort of things. Last time we were kind of being a little more conceptual, perhaps, or to the extent that this class is conceptual, looking at all the various instruction sets and all this stuff. Today we'll try to play with it concretely, and I think there's quite a bit of stuff that gets in your way, like, oh, how do you use GDB here, like with all these vector instructions, and like how do we compile this? How do we get everything to work? So I thought we'll walk through some examples and just kind of play with this and see what we can make it do. Right. So I guess for starters, what is it that the compiler can do for us for vectorization? It can do quite a bit. But why don't we sort of try some simple examples. Let's see. So I think I'll do this on. I'll do it on here. Actually, didn't we have this something we were doing before? Yeah. Okay. So the compiler is pretty good at these things, but it has basically the way it works is by pattern matching of some sort. So if you ask for vectorization, which is once you use the 03 flag, vectorization is on by default, and then you specify which architecture you want. As long as you have an architecture with vector instructions, the compiler will see if usually a loop is vectorizable, right? And then it'll transform that loop into a vectored version. So how do we know if something's vectorizable? Well, first of all, it always needs to be pretty simple. So in this case, it's somewhat clear that each one of these iterations, well, I guess they're not quite parallel, right? The sum part here is an aggregate of all the iterations, but at least the sum is sort of independent of which order you execute these in. Right? So that makes life pretty easy for the compiler. So you could imagine kind of unrolling this loop into wow, that is ugly. Into a bunch of these, and then if we can somehow stick each one of those in a separate element in the vector, now we end up with, over the entire loop, we end up with just one vector full of a few different sums, right? Maybe it's 8 sums, 32 sums, I don't know. And then there will be some suffix code automatically generated, and that takes all of those partial sums and adds them together, and then we're done. It gets harder. It can do quite a bit, but it gets harder when you have. Actually, maybe we should just why don't we just compile it first? Right. Okay, so that will compile it. Oh, that's not a good idea. Let's just see what it looks like. Right, so there's the sort of the busy loop, the tight loop, this part, and then you have your suffix that is adding together something one way or another, getting the sum of all those elements. And that sounds easy, right? Just summing up some elements. And there's one easy way to do it. That would be to write out, so we have this vector of, in this case, we're doing a sum of what? Of unit 64s, right? So that would be 4 of these elements, or 4 integers in one 256-bit wide array. So yeah, one way you could do it is to write out the 256 wide, all 4 of them, to memory, and then read it back from memory into your general purpose register. So you would have 1 write out, and then you would have a 4 adds, I suppose, from memory into a general purpose register. And that would work, but it's not the fastest, because now you have your write. That, I guess it doesn't need to finish, it'll end up in the store buffer. And then you have 4 reads, and each one of those reads is going to take some time, and then we have to add them up. And to add them, we have to actually wait for the read to finish, so you end up with a bunch of cycles there. So in this case, it looks like the compiler decided to do something different. Let's see. I think that this part I'm trying to decide whether this is 32. Yeah, we know how long it is. Okay, so it just went through. It doesn't need a suffix for. If we didn't know how long this array is, how long the loop will be, then we couldn't do it in chunks of 4 elements either. But it looks like it didn't have to deal with that. Okay, so let's see how it's actually adding them together. It's actually unrolled the loop as well here. Right, so we're loading an entire 256 at a time, but then we're storing this, like here we have 4 separate registers that we're doing the adding to, and then again adding to the same registers again. So you end up with 4 different sums, each of which has 4 different sums in them. Right? So down here we're adding them together, right? The individual register sums, and then finally we need to get out of the YMM 0. We have to figure out what's the sum of all of them. So I think what happened here is we're pulling out probably part of the register into XMM1, and then we're adding them together again. So we have this wide register, right, with 4 values. I'll extract 128. Yeah, so now we're getting half of that, 128 bits in a separate register, and we add those together. So now we have 2 sums. And then what is it doing? After we've extracted, there's the add. So now we have 2 sums, and then it looks like we are shuffling. So now you have like the 2 sums, and maybe we just flip them. And so we have the sum A, sum B, and then we flip them, so we have sum B and sum A, and we add those 2 together, then both values will have sum A plus sum B in it. There's the add, and then finally we're moving the value out. Okay, so that's the sort of suffix. Compiler has to do this sort of thing in order to sort of automatically turn what looks like a normal loop into a vectorized loop. We'll see when we write the code and we know what the instructions can do, we don't have to be quite that generic. Let's say we could make sure that our loops are always a multiple of the size of the array, size of the vector registers and such. Okay, so let's see what happens if we put something like this. Right, so if we encounter an element, I guess it was doing this up there too, we missed that part, but that's fine. So if we encounter an element in this gig array that is a 0, then we just stop. So then we get a shorter sum. this is really hard for the compiler to vectorize, right? Because as you compile, you don't know which element will have a 0 in it. So I guess you could. So we would end up like making a sum of 4 more elements. And it turns out that the second among those 4 is a 0. Right? So we added them up, and I was too late. Now we've already done the add. I guess in the case of addition, you could maybe reverse it. You could subtract after, right? And then maybe you could back it up and get back to the correct value. But this starts getting really complicated. And in arbitrary operations, it's not at all clear that you can get back the value you used to have in your accumulator array, or the sum in this case. So let's see what happens when we run this. Yeah, now there's no trace of those V operations anymore. Where's our loop? It's probably like this. So it's I guess we can tell also that the code gets a lot longer with this vectorization. And there's a trade-off there. Right? You need to load the code as well. If you're only going to run a few iterations of it, maybe that's not worth it. In this case, it probably was worth it. Although, of course, if there's zeros in there, we might finish very early. So full of trade-offs. So one thing you could keep in mind is that anything where the number of iterations is not only not known before you start running it, it's certainly not known at compile time. If it's known at compile time, that makes life easier, but it's not necessary. In this case, it's known at compile time, so now we can do it in big chunks. We can unroll our loop easily. We can do these full array assignments or full vector assignments over and over, and we know that it'll be the right number of elements. In the case of an integer, like say we put argc here, so like a passed-in argument, compiler can still do it. Like now we go around the loop until we get close to argc, right? But maybe there's like 3 elements left to finish the job of assigning all these ones. Right? Those last few, they would do in a suffix. So you would have a loop that goes quickly with vectorized, and then maybe separately the last few to kind of make up the remaining piece. So that can be done. But if it isn't even known before you enter an iteration, whether that iteration is the last one, then the compiler can't do it. And the reason then is that we can do part of the work. Maybe we've already destroyed our intermediate values, and now suddenly we realize, oh, we can't do this, so now we'd have to back it up, and backing it up so far is not something that the compiler does. Okay, let's try something else. Oh yeah, I wanted to try these beautiful flags. Let's see. Here. And this only works on Clang. We've mostly been using GCC. And the reason we're using GCC is, for me at least, that I am kind of used to GDB as opposed to LLDB, which is the debugger for LLVM and Clang. But the two are perfectly fine. Both of them they're both very competitive. GCC is an ancient compiler. It's kind of code-wise, it's a mess. If you want to work on a compiler, don't do it. But to use a compiler, GCC is fine. And Clang is getting better every day, and it's. I thought we'd experiment with that now. Apple, in their infinite wisdom, has renamed Clang to GCC. That is a little over the top, I would think. I mean, usually they make good design decisions, but it's a little iffy. I think the idea was, it's not that it's renamed. They kind of I think that they provide sort of a compatibility layer on top here. So all the flags are the same and so on. But I'm not sure. It could be we can just replace GCC with Clang here and everything will still work. Anyway, don't think that I'm using GCC right now, because GCC cannot do these things. Okay, so I told it to remark. This -r is to tell us some more things. So if you loop vectorized anything, tell me. If you missed one, tell me. Right? And then, and this is additional detail on why, I believe. Okay, so let's see. We get rid of that. Okay. So loop not vectorized. Right. So I guess it didn't say anything about this one. I had expected it to say it vectorized it, since I asked for that. Okay, I don't know why we didn't get a remark about this one. Probably should have said that it vectorized it. Okay, so here, why did it not vectorize this particular loop? It doesn't know how many iterations it will go for, because we have a break here that depends on, it's a data dependency, right? So let's try it differently. If we say like this instead, that's also a data dependency in a sense. Ah, okay, so it tells us about that one. Maybe, what could be going on there? The other one. Huh. Oh, okay, yeah. Probably this got converted into a mem set. Like this is some fancy thing going on in the compiler. It's not vectorization. It just decided, oh, all they're doing is initializing this. It's probably got converted into a function call on the fly. So it's not, if we asked for more remarks for other optimizations, probably would tell us about that. Okay, in any case, so here it says, okay, I did vectorize this one. The vectorization width is like, in these vectors we're working with, how many elements are in each? And then there's the interleaving count, which is how many times did we unroll the loop in the, well, unroll this loop. Right? So if we look at the resulting code, see what it did. Okay, so that's our loop, right? So we have the width. These are 256 wide registers, and so we have 60. We have these 64-bit values. Add Q. So that's 4 wide, and then we have a 4 deep unroll. Kind of looks to me like it's 8 deep, honestly. Let's see, add 32. What am I missing? Two elements, it's 8 times, yeah, okay, so it's this unrolled 1 extra time. Huh. Okay, I have no idea. It got it wrong. Okay. So there
were 4 unique registers, right?
That's right. So okay, maybe if we ask for loop unroll, it will say, let's see if we can do that. Pass loop. This loop unroll. Maybe that's a 2. Ah, look at that. Nice. Is it only going to tell us about one thing at a time? It's also a little awkward. But yeah, it would have been nice to get both remarks at the same time. But yeah, there's the extra two. OK, cool. I love this remark thing. It's so great to see what the compiler's, what it's thinking, so to speak. OK, another major limitation is that if you have a loop inside of here, let's see, what do we do? Okay, I'll try that. Okay, so it write to a loop invariant address. Yeah. So anyway, the I guess the main message here. So it didn't vectorize it. Didn't even vectorize this one. And the point is that the compiler can only vectorize the inner loop of anything. So here we have a loop inside of our loop. Can't do it. Potentially, you could imagine if this loop was unrelated to the outer loop, it can move it out. Right? If you're, for whatever reason, you're doing some unrelated computation in here. Let's try that, actually. It could potentially go see if it gets it. Look at that. All right. So it's done some optimization. We don't need to look at the details. Maybe it just cut this whole thing out because we're XORing 4 times. That's an even number, so it's not going to change. Maybe that's it. Maybe it decided that this is unrelated to what else is going on in this loop. It can take it outside and run it there instead. Instruction reordering by the compiler. In any case, if you're doing something like a proper loop that has to stay on the inside here, then the outer loop cannot get vectorized. Okay, I have a little cool example that I wanted to run before we start doing actual coding. What did I call it? Yeah. Okay, so I don't know how many of you are familiar with the Mandelbrot fractal. Maybe all of you? No? All right. It's a cool little thing. Basically, it's so it's a little math formula that describes the boundary between 2 regions in complex space, and it looks like this. Let's see. Actually, why don't we do it on Wikipedia with some proper math notation, just to get the context. It's a fantastic little thing. The math says this, right? So this is an accumulator that starts at 0. This is a constant that is basically the coordinate in some space here between close to 0. It's between like -1 and 1 about in both directions, a complex constant. And so this picture here is the result of running this several times to see, does this value ever go, does the absolute value of this ever get greater than 2? If it If it doesn't get greater than 2, then it's black. And then if it takes some number of iterations, the number of iterations that it takes to get above 2 controls the color. So that's the entire thing to generate this image. And what's really cool about this image is that it has infinite resolution. So anyway, this is not a data or a bandwidth limited application, right? It's not memory bound in any way. This is completely compute bound. So I thought it'd be an interesting alternative. Well, there's some limitations in the sense that we need to write to the screen. But it turns out that this math takes longer, right? We have to do many iterations to find out if it's which color it's going to be and so on. Okay, so the program that does this, if you write it in C++ and you use the complex number functions, it looks something like this. So basically, we're picking for each. Okay. The function says, draw me the Mandelbrot fractal in this rectangle, right, for these coordinates. The original size coordinates are between -1 and +1, about, both x and y. So now we compute this c here, that's the coordinate, right? So it's basically a function of which pixel you want it and what zoom level we have here. And then we have the z, that is the accumulator. So then we run it a bunch of times, and we see if, here, this is the square of the absolute value, if that is still smaller than the absolute value is still smaller than 2, well, then we just do it again. And so we count how many iterations, and that's the entire job. And then finally, when we're done, we set the pixel to 10 times the pixel value to 10 times the count. So that will give us this picture. So now I'm using C++ complex math. Let's do it with full accuracy. And I've enabled all optimizations and AVX. Right? Okay, so it took us 3 seconds. Come on, where's the picture? Oh yeah, here's the picture. Right. And then if I click on it, then it'll zoom in, double the zoom level, make another picture. Okay, so that took us 6 seconds. The only reason that there's, so if you keep zooming in, you'll find that it's this really insane repetitive patterns. It's a fantastic thing. The only limitation to the zoom depth here is the precision of the floating point registers. So we only have 64 bits. So if you use infinite precision math, then you can go forever. You should try some Mandelbrot video if you haven't looked at that. People go like 30 million times zoom and they find cool stuff in there. Math is amazing sometimes. Anyway, it's not so amazing that it takes 6 seconds to generate this thing. So there's a couple of things we can do. First, C++ is very careful about accuracy. So when you work with integers, you multiply a number by another number, or maybe 3 numbers together. It doesn't matter which order you multiply. Or when you add numbers, it doesn't really matter. Like you can do a times b times c, or a times c and a times b, or split them out and make a little tree. Everything produces the same value. But if you use floating point, it's not like that, unfortunately. With floating point math, the order in which you do your operations affects the result, only in the very small details. But if you actually want it to be accurate, you need to preserve the order. You can't do any reordering of floating point math operations whatsoever, which means you can't do any optimizations. Right? So that's not good. But but we can tell GCC, or and this time it is GCC, that we don't care. And so now this means I don't care about the ordering. The small precision changes don't really matter to me. And now it should go considerably faster. So why don't we do a little just for those of you who haven't seen the Mandelbrot fractal.
So it's a repetitive structure.
It is repetitive, but not entirely. Like there's unique stuff all over the place. And then now we have hit the resolution limit of our registers. Okay, so anyway, that took 300 something. And then I found some code and I kind of tried to put everything together. The program is mine, but the algorithms are a mix. So I put together this SIMD version as well, the vectorized version. Unfortunately, the optimizer can't do a very good job of computing this. In fact, let's take a look. Mandelbrot. Yeah. Okay. So we saw the complex version. What are we going to do with this? I mean, there's no translating this into assembly by hand. Just forget it. So the first step, if we want to do anything in sort of hand tuning way, we have to get rid of the C++ part. So here I split it out. This is the same thing, right? But here we have the complex value, the real part and the imaginary part of the complex value. Look, we're all getting a little bit of our math back. Okay, so, all right, so then we're just doing the same computations. Basically, it's just like whatever the C++ would split out into. But unfortunately, and I've spent, I don't know, many hours, because I'm learning many of these things as we go here. I spent a lot of time trying to change this loop to convince the compiler that, well, you really can optimize this stuff. I mean, let's do it vector. It can't do it. This is beautiful for vectorization, right? All of the outside stuff. But unfortunately, this inner thing is not. We don't know how many times around. So you could imagine, why don't we vectorize for each pixel? Right? That was my plan. Right? This looks like such a parallel program. If I have multiple cores, I can just split all the pixels over all the cores, and I get perfect parallelism, and story done, right? But now I wanted to get the vectorization speed up too. And so then it gets a little harder, because now we're running the same instruction at the same time, right, for all the values. Okay, so you could imagine now splitting up. These are easily put in vectors, right? These are just the complex values. That's fine. We can do that in parallel. But now we have this inner loop, and the number of iterations depends on how the calculation worked out. So the compiler can't do that. That's data dependency for the iteration count, and the compiler doesn't like that. Okay, so I tried to drop that. I just said, instead of like stopping here, we just like always go to 100, but remember how many iterations you did. That should have worked, but unfortunately there was another problem, and then that value with how many iterations, what's the deal? I don't remember, but anyway, it turns out that with having this inner loop, there's something about the inner loop that can't be optimized, which means the outer loop, which is perfectly parallelizable in other regards, couldn't be vectorized either. And eventually I had to drop that and go to an extreme case. And so let's see what the extreme case looks like. Mandelbrot SIMD. Ooh, that's not it. Well, it doesn't look very extreme. Okay, so here it is. Right. So the general principle yeah, okay. Right, so here the inner loop is shared for all of the for all the 8 or so pixels that we're doing in parallel. But this test checks that, oh, are all of them done? Right, so we keep running the loop until all of them are done, and then we can safely exit. I guess it's full. How many are there? It's a single precision floats, so that would be 8 of them at the same time. So unfortunately, it gets a little tricky, right? Because now we're dealing explicitly with these, they're called intrinsic functions. So these are the vector instruction wrappers that are provided by C. So essentially each one of these converts into one vector instruction. Okay, so we're not going to look too closely at this thing, but basically here we're multiplying, right? You can see it, sort of. We're multiplying this vector of 8 different pixels, getting the square, and then these are probably the complex values, and then here we're getting the, and so on, right? So we're doing all of them together, and then we have to do, to check, are we done? So here's a comparison, right? And then we keep the values that were, keep only the ones that are not finished yet. Right? So we increment these counters, right, to get the pixel values for the ones that aren't yet finished, and then kind of get ready for the next iteration. Okay, so this, I'm a little dubious about the value of these intrinsics when you get to this this level. The code that comes out isn't pretty, and it's pretty hard to deal with this stuff. So they're called, in this code, they're called YMM11 and so on. These are not register names. These are just variable names. You allocate just variables, and it's up to the compiler to decide which register it actually goes in. You could go to YMM55, but then most of them would be on the stack anyway. It wouldn't give you anything. Okay, so that's an example of sort of how it can go if you want to optimize it fully. And let's see what. So I guess the story there is the compiler, if it knew everything about this problem, could have done it, but it doesn't. It just has some pattern matching things and says, okay, that looks like a good loop that I can vectorize, and it does. But then oftentimes the programmer can still do much better. And so let's see how much better, actually. It took about 300 or so, 350 milliseconds with the fast math. And then we'll do the, and I guess just selecting fast math, that's also a question of the programmer knowing what's going on, right? Because if we do care about this, it would be disastrous to use the fast math if we do care about the fine precision. Okay, so this one was called SIMD. Let's just run that one too. Right, so there it's about 51. And you can tell the difference. It's pretty nice. And there we are out of precision again. Okay, so oh, and how did I do all this, the pictures? Because usually window management is a pain in the ass, right? But I happen to have been working a bit with OpenCV for computer vision stuff, and there's some really nice tools there. So I used some of that. Basically include a bunch of stuff and then very little. There's an image type, this mat, this matrix. You can set points to it. So this is the only thing that draws, right? And then to show it, let's see. Sorry, let me turn that off. To show it is an im_show thing, but that's it. And then to collect these events from the mouse, it's this mouse callback thing. So I'm getting called to this function every mouse click. So this is just as easy as it would be in Java or Python or whatever. C doesn't have to be difficult. Right, yeah.
What's the library called again?
OpenCV. And it has really cool stuff for dealing with images and with videos, and if you want to do any sort of robotic computer vision thing to detect objects and stuff, everything's in there. Not self-driving car level, but that's good stuff. Okay, what were we gonna do? Oh yeah, so I guess next up, I wanted to take a smaller example. There's no way I can put together this Mandelbrot thing in class, but why don't we do a few smaller examples on how to write vectorized code. So let's see. We'll just start a brand new project. We'll call it ADX. There's a couple things you need. Generally speaking, we need a bunch of these intrinsics. Right? So now we may use some of those intrinsic functions, the C-looking functions that you saw. Or we may just do this with inline assembly. We'll do a mix, but generally speaking, you need it at least for the types. If you want to have inline assembly, you need to be able to pass the inline assembly a vector value, and those types are from in here. Okay, so we'll just do this. So why don't we start with our simple little something that we had before. The alignment isn't actually important here. We can drop it. Oh yeah. So I thought we'll do this over characters now. So we have this thing full of unsigned characters, and we just want to see an unsigned sum of all those. So we'll start with the standard. Actually, why don't we do it like this? So this is for reference. And I thought we'd also do some timing. And I don't know if I discussed this before. This RDTCP, I think I mentioned it. It's a read timestamp counter. That comes out of the x86 intrinsics. It's not vector related, but it gives you just a cycle count. P is important. The P, in part, it writes the processor number into this variable. We don't need it, but that's just what it does. P is also an ordered instruction, so the compiler can't, sorry, the processor can't run it out of order. And that's relatively important if you want to measure time. We shouldn't just measure the time after we've done the work, or vice versa. Okay, so do it this way. S and 4 minus, no. Okay, let's just do that one. Really? What's wrong with it?
I think you call it AVX.
Oh, that's why. Thank you. I should call it AVX here too. Okay. How is the sum 1?
Did you say?
That's kind of funny. I mean, I didn't initialize it. This one here probably is where the 1 came from. Let's see. Yeah. This here couldn't have had a 1 in it because this is allocated in the VSS segment of the file. It's guaranteed to be allocated from the kernel, and the kernel always clears memory before it gives it to user space. But S here was allocated on the stack. Stack is full of garbage, so we got a 1 garbage. Okay, so it took us 400,000 cycles. And that's 400 million cycles. I guess that's kind of fair enough. Let's take a look at the code. So it's nicely optimized one way or another, or vectorized. All right, let's try this. So we want to do the same thing, but let's just do it by hand with our intrinsics. So we'll just do another. It's kind of ugly. Okay, so we have 2 of them. So now, what are we going to do? Now it starts getting a little interesting. So we want to use vector instructions, but with the C functions. No inline assembly, but we want to now add together, I guess it's 32 of these elements at a time. Right? So I guess we want to start with, we need a sum. M256 sum. And in fact, there isn't a good way to initialize it, I've found. There isn't like a C initialization, like you can't say this. Or in fact, maybe 64-bit, it's possible that it'll actually do this. So let's see if it accepts that. That'd be nice. Yeah, it looks like, okay. So now we're giving it 64-bit values. So there isn't, like, if you want to initialize this with byte values, there isn't a good initialization function or like a static initializer way of writing it, I think. Yeah.
The error was that S is not.
Yeah, exactly, right, yeah. So I wasn't worrying about that. Yeah, so it accepted this initialization. That's fine. Okay, so now I guess we want to say we want to add these together. How do we go about this? Right now we need to find a function that does this. And so far we've looked at the instruction set, and if it was the instruction set, I think I would know what to do. It would be kinds of vector parallel add, and then and we wanted to add it byte-wise. So I think VP add B probably would do it. And then I would specify the 3 registers, the 2 sources and the destination. That'd be great. But unfortunately, it's not going to work now. So we have to go look for the correct intrinsic function for it. And I found a beautiful little cheat sheet. It doesn't have everything. We could dig through the mmintrin.h, but unfortunately, it includes a ton of other files. And as you know, like this thing evolved over more than a decade. And so the AVX2 stuff includes stuff from MMX, and we wouldn't know where to look for the function. And we don't even know what it's called. So it gets a little tricky. But this cheat sheet was very nice. So what did we want to do? I think we wanted to start with a let's see. So we have our array. Yeah. Okay. So why don't we want to add. Where are they? Arithmetic, addition. Oh, there. Okay, so that's about it. So this EPI is extended. Don't know what the P stands for. Integer. It's basically just integers of various bit width. And these MIs, those are any vector type. So we'll say. How does it go? In fact, I think you have to start with yeah. And so it starts with MM256 like that, and then we say add, and then EPI, and we wanted EPI 8. So our sums is the sum of this, and then we want to read something. So we got to get that value out of our I think we can do this. Where is it? Array I. It's a good chance we need to cast this. Let's try without. No, we're going to have to cast it. Why don't we do... yeah, I'll say it like this. M256. Close. Okay, a little more readable that way. Okay, so what's going on here? Take the address of the array element that we're interested in. In fact, now we're doing this 32 at a time, so it should be this equals 32. So now we're pulling out 32 elements into vals here. Right? That's the address of the correct element. But we're saying, oh, by the way, that's a 256-bit value pointer, and then we dereference dereference it to get the value. So I could have stuck all of this inside of there, of course, but that maybe a little too much in one line. Okay, so now we have after we've gone around this, finish it. Sums here has 32 different sums in it, right? But to get the value to return, we have to compute the sum of those sums. So fortunately, it's a pretty small array now. It's only 32 bits. So we could do, we can treat this sum as an integer, as a set of characters, and go like this. Sums goes address of okay, what's going on? So this here is a 256-byte value packed bytes, right? I take the address of it. I say, oh, by the way, this is address actually pointing at just bytes. Probably you should do unsigned here. I think we're dealing with unsigned everywhere. Right, unsigned. So now sums here is just a character array. Why don't we do unsigned? And I'm just going to sort of cheat and do this with scalar math. Because it's 32 steps. And we're going around the other one for like hundreds of millions of cycles. So who cares about 32 steps? But you could, if you're a compiler, you could try to be a little more clever. Like shift everything by one value, by one offset, and then add them together and shift again. Or there's things we could do to shave off a few cycles more, but let's just leave it alone. Final sum.
Where do you declare sums?
Here.
And you used it in the loop though above that. Was that supposed to be sum up there?
Oh, thank you. Yeah.
And then before it as well, before the assignment. No, next line.
Oh, there. Yeah, thank you. I guess there are sums in there. Maybe they should be called sums, but then the next one would be sums. Yeah, okay, lots of sums in here. All right, but it doesn't look that bad, this one. Question is, what does the code look like? But let's try running it first. Did I call some in trin here? Yeah, I did. Good. I'll start by running it. Is that anything important? No. Oh, this one. That is probably important. Oh, I see. Those are floats with an I. It's treated as a collection of integers. Otherwise, it's a collection of floats. And you can also put a D if it's a collection of doubles. What more are we missing?
Underscore in front of the
Okay, pretty good, but let's, we're missing another sum here, S2, and yeah, okay. Okay, that's not too bad. Looks like we scored a little improvement. 32 million versus, ooh. No, that seems like too much of an improvement. 32 at a time. Did it not vectorize, maybe? Am I compiling with, with 03? Okay. All right, let's take a look at the code, see what's wrong. I'm hoping we could get to a little bit of GDB before we're done too. Okay.
What is wrong right now?
I think that this code was way too much faster than this one, because this ought to be nicely vectorizable by the compiler, but this was 10 times faster, or something like that. So what's going on? Interesting. See. Oh. Was I running the wrong one? Compiling to the wrong one or something? Kind of lame that the sum is always 0 too, isn't it?
I don't know if this really matters, but are we measuring from the time, the second, should there be a second before?
There are, that's the after here. Like, so I'm just using these two for one of them. So I think that's okay.
Yeah.
Let's see. And they're, what are they called? They're called val? Array, yeah. Okay. Just to... Where's the Q? There, thank you. Really? But it could be that they all add up to. Yep. They all add up to, because it's a billion of them, it turns out that they all add up to the same, to a 0, right? That was a little unfortunate. I'll just put a percent 129 in here, and now I think we're done. Now we should get interesting values. Yeah, okay, good. Surprisingly close. But anyway, oh. Is there something wrong with our time measurement here? Because now they look correct. I wonder if the compiler decided to get really clever and see that we didn't actually initialize that array, all right? And maybe in one of them it made use of that, and the other one it didn't. Maybe that's what happened, because this is looking reasonable. Okay, so 200 million cycles to add up a gigabyte. That seems pretty okay, right? That's 100 milliseconds per gigabyte, so we can do 20 gigabytes per second. That is the bandwidth limit on for memory. So we're going at a good clip. Okay, but what if we wanted to, actually, I think we should probably switch to GDB. I want to write this in full-on assembly too, but let's first see what it looked like. So this is nicely vectorized. Where's ours? Sum in trin, it's this one. And this is our code. It's kind of hard to recognize it, because it's doing a lot of register allocation and a lot of unrolling and stuff like a C program would, but now it's also full of all this other vector stuff, which is a little hard to grasp. So how about we write it in plain assembly, and maybe we'll do it in, take a look at the GDB next time. I think the assembly will be pretty quick. So we'll just do the internals here. Tight loop is the one we're interested in. It's a good idea, generally speaking, to use intrinsics and C for everything that isn't like really important. The assembly stuff, and especially vector assembly, hard to maintain. So let's just do a little bit of it. So what's the deal here? We have our values. In fact, we can stick that in as an input, because also just, okay, so reminder, I want this in plus x. Okay, maybe I'll leave it in here. We'll say vals here. Okay, reminder, here's the code, right? And next comes the outputs, and possibly outputs and inputs between the columns. And the next constraint is just inputs. X means this is going to go in a vectorized register, or vector register. And then finally we have our clobbers at the end. Okay, so what do we want to do? We wanted to add to the sum, right? So that's going to be an output and an input. Plus means it's both. What is this extra thing? Okay, get rid of that one. So now we're going to get this in %0, this value, in some YMM register, but in %0. This will be some YMM register in %1. And so to do our add, as VP add B, probably. Let's take another really excellent reference that I found. This one here. Felix Cloutier. Cloutier, I don't know. Add. Is there a vector add? No, it's a P add probably. P add, yeah, for parallel. Good. So we wanted to add up the bytes, and then with the V prefix, V add B. That's the one with 3 arguments. So we're going from our sum to our from our sum and our vals back to the sum. Okay. So let's just see how that works out. I'll replace it in here for now. Yeah, it didn't like this. Hard to blame it. Junk. Oh. Okay. Sadly, not much on improvement. I think next time we'll have to take a look at something where we can make a big difference. Let's see what the code looks like. Let's see. Some ASIN, right? Right. Okay, so here it is. That's our tight loop. From there to there. All right. So we have our move. That is this part. Right. We're moving the value from vals here, right? This is what's moving into YMM1. We have our add, which we just wrote here, and then that's the next addition right there for the loop around. So now we have a good grasp on what code we're actually generating. Next time we'll take a look at a little more complicated application, just how we can kind of puzzle together a vector program out of all these instructions. And we'll play with GDB as well. So it has some really nice facilities for this stuff. Okay, that's it. Don't forget about the homework. It's due on Tuesday. And have a good weekend.